So today's daily problem is called minimum number of k consecutive bit flips. It's quite easy to understand. You're given a binary array nums and an integer k, and a k bit flip is choosing a subarray of length k from our array, and basically just performing an XOR on all elements, meaning if any element is 0, turn it to 1, if any element is a 1, turn it to 0. And in the end, you just want to return the minimum number of k bit flips required so that there's no 0 in the array, aka you transformed all of them to 1s. So in this case, you can only change bits of length 1, so obviously you'll change this one and this one, so it takes 2 flips. In this example, you can't really change it, so if you change these two, then this will have a 0, and no matter what you'll do, you'll always have a 0 in the end, so you return -1. And in this case, if you follow these three, you'll eventually get all 1s with 3 flips. When it comes to this problem, it actually becomes pretty greedy in the way that if you ever come across a 0, well, you have to toggle it, because if you just move on and toggle this one, well, this is only going to affect everything else, so this will be left as a 0. So that kind of just indicates that whenever you come across something that needs to be toggled, you have to toggle it. Okay, so in this case, like if we see a 0, well, we have to toggle it, meaning that these will actually be toggled to 1s. And then now when we come across here, well, this is already 1, this is already a 1, this is already a 1. This is a 0, so it needs to be toggled. But how can we sort of know that, well, we toggled this one. How do we know that that toggle didn't affect this? Because yes, we know that it's a window, right? And that's sort of where the sliding window concept comes in. So how are we going to know here that this one did not affect it and this one did not affect it? How do we know that? Well, we have to keep maybe count of something called like a flips counter, which I'll initialize to 0. And this is just going to contain how many flips have been done. Like let's say we're looking at like this element. Well, it's just going to look back up until the last, I guess, k elements within that window. And flips is just going to tell you how many times there has been a flip within this k window, because that's all that matters. But how are you going to do this? And how do we know, like, if we're looking at this index, we know we flipped this one. So how do we know that this flip did not affect that? Well, we can use a, as we kind of traverse through, we can use, like, booleans. Like, in this case, we'll say, because we flipped it, we'll put it as true. And then these ones, well, we didn't have to flip it anymore because they're 1s. And then this is our window currently. Now when we're looking at this element, well, our window is going to shift. Because our window eliminated this element, well, because of this element, we knew that before we had flips being 1, but because we just eliminated it from our window, well, we know it has been flipped because it's indicated by this true. So then that means we can actually minus it, so now it becomes 0. So when we're looking at this window, or rather this index, we see that, hey, nothing has been flipped, so therefore 1 is fine. Since it's 1 and it hasn't been flipped, that means you can just move on. However, if this was flipped, like for instance, let's say this was a 1, so that means you don't have to flip here, but that means you have to flip here. Now in this case, flips would be 1, and in this case, this would be a 1, so that's fine. And then when you look here, well, flips is a 1, and this is a 1, meaning that this would have been a 0, so you have to flip here. So the general rule of thumb is if you look at any index and you see that flips mod 2 is equal to this guy, then you have to flip this. Right, because if it's a 0 and you have an even number of flips, then you have to flip it. And conversely, if it's a 1 and it has an odd number of flips, you also have to flip it. Any other case, you don't have to flip it. So that's basically the general rule of thumb. One last rule of thumb is that if you ever come across a 0 and you realize, hey, I know I have to flip this, but because k is 2, that means I have to flip the one after it. But in this case, there's none after it. This is the only case where this would actually be impossible. In this case, we can return -1. So this is the one edge case. Other than that, we have everything we need. Alright, to start this question, hopefully this would explain it a bit better than the drawing solution, but we'll initialize our resolve variable first, kind of denoting the minimum number of k bit flips we need. So in this case, we're going to return this at the end, and this should be minimal. Then we're going to initialize flips, and this basically just keeps track of the number of flips within the current window. And then we're also going to have a boolean called flipped, which is all going to be false. And the ith, what this kind of helps with is the ith element will be flipped if this is true. And the reason why we need this is, again, because if we're kind of looking backwards, if our window is shifting, we got to look at the I minus kth character and see, well, was that character flipped? Because if it was flipped, then that must have contributed to our window flipped variable. So because we're excluding it now, we want to check if the I minus kth character was true, aka flipped, and if so, then we have to decrease this by 1 because it's no longer in our window. Okay, so now we can actually go through the algorithm. We're just going to traverse left to right and say, well, first we can check, well, if I is greater than or equal to k, this kind of means that the window shifting started, so we'll have to do some special casing for here. But in the general case, we just want to know, we're looking at the ith character. Does that need to be toggled? How do we know if it needs to be toggled? Well, it's if flips mod 2 is equal to nums at I. This is a bit of a clever way of doing it, but all this says is if you have an even number of flips and the number is 0, that means you have to toggle it. Also, if you have an odd number of flips and the number is a 1, you also must toggle it. So this just checks that you must toggle this ith character. So if you have to toggle it, that means your flip should increment. I guess your res should also increment because you flipped the number. And also we can denote that this character has been flipped by just setting it to true. Okay, now let's get back into our window shifting. So if we know that the window is shifting, well, flips can possibly decrease by 1. How do we know? Well, it's if flipped at I minus k was flipped, aka if it was true. So if it was true, because we're excluding it from our window now, this will decrement by 1. And that's it. I guess the only case that we haven't considered now is if the output is -1. And when does this become -1? Well, it's if I plus k, I guess -1 for indices, is greater than or equal to length of nums. And like this example suggested, because we're trying to toggle this character at index 2, let's just suppose k is 2. So therefore, it's saying I need to toggle something at index 3, but there is no index 3, right? Because now it's greater than or equal to the length of nums. That basically just means you can't do it, so you have to return -1. So yeah, I believe that's all the code, so we can run it. And it seems to be working. And yeah, pretty solid. But there is one improvement that we can do really quickly. So in this case, we used linear time and space. But do we really need linear space when we realize that, hey, we're only really checking one element at each iteration? We're not checking like a group of elements. So we can actually just replace this with a variable. Rather than saying this element has been flagged, so we're saying it's true, why don't we flag it with some other thing? So we know that nums only contains binary, but what if we say it equals 2? In that case, now we can just check, well, if nums at I at minus k was a 2, that means it has been flipped, so then we can just use that instead of this flip variable. And yeah, I think this should still work, and just like that, we reduced our space to constant space, so O1 space, and yeah, it seems to still work. So yeah, I hope you enjoyed.